Okay, hello, and welcome to week 5 of Social Science Research Methods. Today, we're going to talk about hypothesis testing, and things are going to get a little bit more complicated. So let's just jump in. When we talk about hypothesis testing, we're talking about testing a claim about the population using a sample statistic. And I want to be clear here that we're not talking about coming to definitive conclusions. Instead, we're talking about calculating the probability that a member of the population um, meets this particular parameter that we've derived from the sample statistics. So up till now, we've been dealing with sample statistics, and now we are moving to population parameters. We did a little bit of that last week when we got into z-scores, but now we're really going to start doing it. So how do we do this? We do it using something called the central limit theorem. And I'm not going to get too in depth about what the central limit theorem is and the equations that are used to come up with a theory, but I am going to tell you that essentially it means that you can use these sample statistics that we've collected from small representative portions of the population to make inferences about the population as long as we're using a standard normal distribution. So a normal distribution is that of a particular variable where you're plotting all of the individual sample statistics around a particular mean. A standard normal distribution is one that theoretically standardizes those scores around a curve where the mean equals 0 because we're trying to be able to apply it to all variables theoretically. And we do that using z-scores, and we got introduced to z-scores last week when we were calculating the upper and lower limits of confidence intervals. So we use z-scores to test our hypotheses and transform them to t-scores as a part of that testing process. And when we transform z-scores to t-scores, we're moving from, in the denominator of the z-score equation, the standard error of the population, sigma y bar, to the sample estimate of the standard error, which is the standard deviation divided by the square root of n. Now I want to stop here and say, you can see that the reason that we're standardizing, quote unquote, these scores is because now we have moved literally to standard deviation. And on a standard normal distribution, we use standard deviation to talk about an individual score's distance from the mean. So we'd say 1 or 2 or 3 standard deviation units away from the mean as a way to talk about distance rather than specifying within the categories of the variable itself. So we use a t-score now equation to compare against a critical value of z, and we'll come back to that concept in a second, using this formula here. T sub I equals y bar, the mean of the sample, minus mu sub y, which is the mean, the theoretical mean of the population. Maybe not theoretical, hypothetical, since we're talking about hypothesis testing. The hypothetical mean of the population divided by the sample estimate of the standard error. Standard deviation divided by the square root of n. Okay. Hypothesis testing, remember I said, is about probability. Specifically the probability of obtaining a particular sample statistic if a population has this hypothesized parameter, population parameter. We notate our hypothesis using H sub 1, the research hypothesis, the thing that you believe to be true, and H sub 0, the null hypothesis, the thing that you do not believe to be true and are therefore testing to hope to reject. Now, how do we come to decide what these hypotheses are going to be? Well, that depends on you as the scientist. What existing research and literature have you read that helps provide guidelines for what sample statistics you would like to test? That is, it'll be based on maybe even your personal experiences or things that you've seen if you're doing more inductive research and haven't sort of formally looked through the existing research yet because you don't want to have, in this case, sort of particular preconceptions about what your findings are going to be. So in this example, you can see that we are testing the hypothesis that a student at the University of Minnesota has a GPA relative to 3.0. And when I say relative, I mean we're either testing the directional relationship, so greater than, less than, or equal to, or a directionless relationship, so just is it equal to or not 3.0. H sub 1 is mu greater than or equal to 3.0, and H sub 0 mu less than 3.0. You can see here that these two symbols are exhaustive. So we've exhausted all of the possibilities, all of the potential numbers around 3. That is a directional hypothesis test. And down here, you can see that we have mu equals 3 or mu does not equal 3. That's when you're testing and you are uncertain about the direction away from or towards the particular sample statistic that you're looking at, and so you want to look on both sides of the standard normal distribution. Okay, what if we're making the wrong choice? That's something that we have to consider as social scientists. And so in particular, as a part of the hypothesis testing process, we're trying to understand the probability of a type 1 error, incorrectly rejecting the null hypothesis. And remember, in hypothesis testing, our goal is to be able to reject the null hypothesis, the thing that we do not believe to be true. In order for us to test this, we create these particular probabilities of type 1 error using alpha, a new symbol for us. Alpha equals 0.05, alpha equals 0.01, alpha equals 0.001. And when we talk about alpha, what we're talking about are the spaces on a standard normal distribution at the ends of the curve, in the tails, we call them. And that is where the anomalies sit, right? So if we're talking about a standard normal distribution, we would expect most of the responses to be around the mean, and our research hypothesis should reflect that. And in order for that to be true, we have to reject the idea that most of the responses are in the tails, and we do that with these alpha areas. Okay, let's stop here and talk about your z-score table, because that will be very helpful in understanding alpha areas. You can pull up your z-score table now on Canvas in the File section, week 5. I'll give you a second. Okay, you'll notice on this chart that there are 3 columns. We are really interested in the third column mostly. That is the area under the standard normal distribution from z to infinity. So the first column is the z-score itself. The second column is the area under the standard normal distribution from 0, which is the mean, to that particular z-score. And that would tell us something about the area around the mean. We're interested in column 3, which tells us something about a particular z-score to infinity through those tails. Remember, that's what we're trying to project. For the 3 alpha areas that we have, 0.05, 0.01, and 0.001, there are 6 corresponding critical values of z, and you can find those in the first column of your chart that you need to know. 1.65, 1.96, 2.58, 3.10, and 3.33. 1.65, 2.10, and 3.10 are all alpha areas for one-tailed tests, meaning that the area is just from z to infinity. The other 3 are for two-tailed tests, where you take the alpha area and you divide it by 2 to find it in the chart, the corresponding critical value of z, because you're splitting that area onto both sides of the normal distribution, because it's a two-tailed test. It's on both sides of the curve. I would write down those 6 numbers somewhere and remember them, because they are the critical values of z that you will always use in hypothesis testing for this course and for intermediate and advanced social statistics as well. Okay, I was talking about directional and directionless before, and I just alluded to the fact that we talk about these as one-tailed versus two-tailed tests based on what tails they are in the standard normal distribution. So a one-tailed test is those directional tests that we talked about, notated in your hypotheses with greater than or less than, or greater than or less than and equal to. And two-tailed tests are on both sides of the standard normal distribution because they're directionless. You as the researcher are not exactly sure where on the standard normal distribution particular scores will find themselves, and so you're looking in both tails. It is a directionless test. You're going in both directions. Okay, let's look at this example of a hypothesis test about the usefulness of ramp meter lights in Minneapolis. We have these in Pennsylvania too. They're meant to keep the flow of traffic on the freeway moving as people are merging on, especially during rush hour, which we don't really have right now because of COVID-19. But social scientists in Minneapolis were involved in this testing when it was taking place, and they came up with these research hypotheses, one from a politician, one from an engineer, and you can see directional versus directionless. Okay. When you're doing hypothesis testing and you are talking about alpha area, again, those values 0.05, 0.01, 0.001, what you're talking about is the size of your confidence in your rejection of the null hypothesis. So 0.05 has the largest area under the curve from z to infinity of the 3 values, which would mean that there's a higher likelihood that individual sample statistics would find themselves in those tails than at 0.01 or 0.001, where the area is really small and there's not a high likelihood that a lot of the population would even be able to fit in there if you want to think about it visually. So when we're doing hypothesis testing, what we're trying to understand is where is the calculated t-score that we're going to talk about how to do in a second relative to the areas under the standard normal curve that we're looking at our particular alpha areas. Okay, stop here. Take out a piece of paper that you are not going to lose and write down this process of hypothesis testing. Come back to it every time we have a question about it. It will help you, I promise. So you first start with your hypotheses, both a research hypothesis and a null hypothesis, and we said that there are lots of different ways that you can come to what those hypotheses are. It's up to you as the researcher. Then you have to pick an alpha area. So how confident are you? We'll talk about confidence intervals a little bit more next week, but alpha areas then correspond to confidence levels. But before we get to confidence levels, let's just think about size. 0.05 is the least confident that you can reject the null. 0.01 is a little bit more confident, and 0.001 is the most confident. So pick one of the alpha areas based on your overall confidence as the researcher in the power of your research hypothesis. And then you want to identify the corresponding critical value of Z that we talked about that you find on your Z-score chart. It's always going to be one of those 6 numbers that I gave you before. Now, we're going to stop and calculate our T value. So remember that T is the Y bar, the sample of the mean of the sample, minus mu, the theoretical mean of the population, divided by the standard deviation of the sample, divided by the square root of n. In most cases, you will either be given or have the tools to calculate Y bar. Mu is the theoretical population parameter that you use as part of your hypotheses, your research and your null hypotheses. So you plug those numbers in there. Standard deviation and n are also sample statistics that you either will be given or be given the tools to calculate yourself. N is not something that you necessarily generally have to calculate. You use orders of operation to come up with a t-score. Now, you use that t-score, and I would physically map it onto your standard normal distribution to find out if it is within that area under the standard normal curve that is associated with your critical value of Z at the alpha level that you've chosen. So, for example, at the alpha level 0.05 for a one-tailed directional test is 1.65. So if you were to map that onto a standard normal distribution, any value of t higher than 1.65 is going to find itself in that region of rejection. So we can reject the null hypothesis. If it finds itself outside of that, then, yes, that's right. If it finds itself outside of that, then we cannot reject the null hypothesis. And again, that is about alpha area and type 1 error. Once you make a decision about rejecting or not rejecting the null hypothesis, then you can come to this probabilistic conclusion about the relationship between the sample and the population. Okay, here is another example of research hypothesis. I'm not going to go through it with you, but I just want you to stop, take a moment to make sure that you understand how and why these hypotheses are noted the way that they are and what that relevance is to the social science research question that's happening here. Okay, Let's do some practice now because I have given you a lot of information. So this first one here is hypothesis about median household income. I've given you all of the sample statistics. You just have to identify a critical value of Z, calculate the t-score, and then come up with your probabilistic conclusions. Give it a shot. Okay, here's one more example using sex frequency variable. Again, you have all the sample statistics that you need. Take a few minutes, pause here, and try to complete this one. I'll give you a second. Okay, we always have to have a proportion example, and so I have provided one for you here. Take another few minutes and give it a shot. And last, but definitely not least, because it is a bit more complex, let's try a two-tailed hypothesis test example. This is the last example that I have for you today, so you can stop the video here, spend as much time as you need trying to answer this question. As always, notate anywhere in the lecture where you have questions or you are unsure about the process of hypothesis testing. Bring it to discussion, and I will talk to you then. Bye-bye.